Okay. Well, greetings once again. I guess in this lecture I was supposed to discuss the Goldstone boson equivalence theorem, but I regret to say that I didn't cover some material in the previous lecture, which is going to be relevant later, and it's actually also interesting. So let me take 15 minutes out of the other discussion to finish yesterday's lecture. So in yesterday's lecture, we talked about the precision tests of the electroweak interactions. And I showed you that SU2 cross U1 is in extremely good shape. It was tested in these experiments with 20 million Z bosons created individually at rest and studied in detail. And in those measurements, and also in measurements that I didn't mention yesterday, the precision measurement of the W mass, one confirms the prediction of the electroweak theory to fractions of a percent. It's really very impressive work. So now there's one more thing I wanted to talk about, which is something that got started early in that program when there was still hope that one might discover physics beyond the standard model from deviations in those measurements. And unfortunately, physics beyond the standard model was not discovered in those measurements, but nevertheless, this theoretical technology hung around, and people have thought it was useful. So I'd like to explain it to you. This is the question of how you would parameterize a deviation if you discovered one. So to introduce that, I need to basically say a few things which are a little more sophisticated that I didn't say yesterday about the SU2 cross U1 theory. So the SU2 cross U1 theory, as I told you yesterday, has basically three parameters, G, G prime, and V, which if you basically at the tree level, that defines all the predictions of the theory. At the one loop level, other parameters come in, such as for example, the quark and lepton Yukawa couplings. But to renormalize one loop diagrams, basically what you have to worry about is that these three parameters are renormalized, and so they can be shifted by one loop diagrams. Formally, these shifts are infinite, and then you would renormalize them by reference to some observable quantities. And it's a little hard to see how GG prime and V can be directly observable. I mean, you can make some complicated definitions. But typically what you do is that you choose some observable parameters, some parameters you can which are really very close to measurement and experiment. And then you would fix those parameters. And then in the process, you would remove the infinities from the theory. And then, using those processes as a reference, you could then go through and calculate any one loop diagram, referring the infinities in that diagram to the choices that you've already made. So there are various ways to do this. I think the original one that was done really carefully was the Marciano and Serlin definition. And that definition uses alpha renormalization group run to MZ, MW and MZ as three parameters that you would measure. And then those parameters, if you compute them in perturbation theory at one loop, you have infinities. You would then define the infinities by saying that the bare parameters plus the one loop contributions give you the observed values for these three quantities. And it would turn out that that would then remove the rest of the infinities from the theory. Because, well, these are the only infinities that there are in that theory at the one loop level. Corresponding to this, it's very interesting to have a value of the weak mixing angle, because that appears ubiquitously in all expressions. And so Marciano and Serlin define sine squared theta w as 1 minus mw squared over mz squared. And today this is a number which is about 0.227, I think. Now, there's another way to do it, which seemed to be the right way to do it when the Z0 experiments started, which is to choose alpha of mz, G Fermi, and mz as the three basic parameters. And this is a great thing at that time because MW really wasn't known very well in 1990, but G Fermi was known to 5 significant figures. So this is like 5 significant figures, 5 significant figures, and then when the Z resonance was measured, that was 4 significant figures. And then you could really make very accurate standard model predictions on that basis. And so for that, there's some different definition of sine squared theta w, which one can write in the following way. For example, you could write sine 2 theta w squared, which is equal to 4 SW squared CW squared. And I'll denote this with a 0 because it's going to be different from that one, is equal to 4 pi alpha divided by root 2 G Fermi mz squared. And if you work it out, this set of quantities at tree level will evaluate to this, and then you can then use that as a definition of sine squared theta w. So let's call this sine squared theta w 0. There's another definition of sine squared theta w that you could use, which is to measure, for example, the leptonic asymmetry, which is very sensitive to sine squared theta w. At tree level, the relation is 8 times 1 minus times a quarter minus sine squared theta w plus some small corrections. And so if you like, you could just make this a definition and call that sine squared theta w star. And each of these is a perfectly legitimate way to renormalize the theory. It's just it leads to different intermediate expressions. But when you relate observables to observables, everything has to work out and give the same predictions up to, for example, some neglected 2-loop terms, which in electroweak theory are 10 to the minus 4 effects. These two values are in quite close agreement, and they're both equal to about 0.23. And so that's what I like to do. But many of you, actually I'm surprised that nobody yesterday said, why did you take sine squared theta w equal to 0.231 when everybody knows that sine squared theta w is 0.227? Was anyone tempted to say that? No. Well, it does depend on the energy, but that's not the important effect. At the LHC, one has fantastic measurements of mz and mw. And in fact, mz and mw are the basic things that you work with. And there are many LHC calculations that depend on the relation mw equals mz cosine theta, which is a tree level relation in the standard model. And many of you know that there are cancellations in electroweak amplitudes at the LHC, which basically are proportional to this quantity being 0. So for various reasons, this is a very useful definition for LHC physics, maybe less so for E plus E minus physics. In any event, I'm not going to advocate one of these over another. I just want to be clear that there are different ways of renormalizing the theory, which can be codified as different definitions of sine squared theta w, and they're related to each other by one-loop corrections. So they're basically things that happen in the second or third decimal place that separate these. But nevertheless, they're distinct physical quantities, and it's interesting to be aware of that. Okay, now, oh, I gotta get rid of this. Yeah, good. Okay, now we can start to talk about, oh, and there's one more definition of sine squared theta w, which is used by the particle data group, which is none of these. It's ms bar subtraction. And so there's a sine squared theta w ms bar, which is different from all of these numbers. And so whenever you read about precision electroweak, you have to be very careful what value of sine squared theta, what definition rather, people are talking about. Okay. Now, in this context, we can then introduce some terminology for talking about corrections to the electroweak theory. And this is something I was very interested in at the time these experiments were done, because I was a fan of a model of beyond the standard model physics called Technicolor, where the Higgs was a bound state created by new strong interactions with a scale of 1 TeV. And so Technicolor was definitely on the outs at that time. It had many recognized problems and no solutions, but no one could quite succeed in killing it off. And so with Takeuchi, we had a certain class of ideas about how to do that, which turned out to have a nice generalization. So what we said was the following. Let's think about processes like E plus E minus to a Z boson going to FF bar. And let's think about beyond the standard model effects that would change this diagram by radiative corrections. So for example, if you had supersymmetry, you could have the supersymmetric partner of F here, and you could exchange some kind of neutralino here, and there would be a correction of this form. Or you could have some kind of extra Higgs boson participate in this channel. Let me call it capital H. But typically, these effects were very small when people computed them. They're 10 to the minus 3 level or smaller. On the other hand, there's another kind of radiative correction which is quite generic, which is to insert some kind of vacuum polarization diagram in the Z line. And in fact, there are even diagrams like this, which have photon Z mixing through one loop effects. And those diagrams, it turned out, often had a large effect, for example, on the value of sine squared theta W that would be measured in the Z asymmetries. So we decided to define a class of corrections called oblique corrections, which would exactly represent the effect of beyond the standard model in theories of with the following definition, that we were interested in theories for which the beyond the standard model physics did not couple to light fermions, but it only coupled to W bosons, Z bosons, and Higgs bosons. And maybe photons, of course, if it were charged. So that seemed a very sensible thing to think about, because after all, the purpose of new physics, in some sense, was to explain the Higgs boson. And so the Higgs boson couples very weakly to light fermions, but it couples with ordinary strength to the gauge bosons of the standard model. And so basically, this is the assumption that all BSM effects on precision electroweak come from vacuum polarization diagrams. So it turns out that it's not exact because, of course, there are effects like this, but it's a good approximation. It makes life really easy. And one of the advantages of making life easy is that you can do things in great generality. So in particular, there are only 4 vacuum polarization diagrams in the electroweak theory. And so let's just analyze them. So here they are. There's the photon-photon vacuum polarization diagram. Then Z photon, etc., and WW. And I'm going to represent those in the following way. By writing Q as the electromagnetic current, 3 as the third component of weak isospin, the SU2 isospin. So there's a 3,3, a 3Q, and a, and let me say 1,1. So 1 plus I2 is the positive W boson. Let me keep it 1 so that the normalizations are symmetric. And so this would be the current matrix element, J mu Q, computed from, well, in this case, one loop diagrams, although we might as well compute them in any way we wish. In principle, there could be, if you had like technicolor interactions, new strong interactions, there might be strong interactions inside this bubble. But then we can try and analyze these contributions. Now let me add one more assumption, which is that new physics is heavy. That is to say, the scale of new physics is much larger than the mass of the Z. Then it also makes sense to Taylor expand these expressions in powers of the Q that runs through the diagram. So if we Taylor expand, this is a new physics contribution, we get Q squared over M squared and Q to the 4th over M to the 4th. And if Q squared is much greater than M squared, let's say new physics is as high as 500 GeV, then we can neglect the 4th power and we can expand this out to order Q squared. Now, as you know, the vacuum polarization diagram of photons is 0 at 0 momentum. So this actually begins in order Q squared. Here, there can be a contribution at 0 momentum, and then there's a Q squared term, etc. Here, there can be no contribution at 0 momentum because the Q is conserved. So this diagram only has to be conserved on one side. So if this is 0, then the diagram has the form Q squared G mu nu minus Q mu Q nu. And so that means this coefficient vanishes. So there's a D. And then this one, there's a finite value, E and F Q squared. And I'll neglect terms of order Q to the 4th. So there are 6 coefficients here. However, these 6 coefficients include some effects that I'm already dealing with because, for example, this coefficient and maybe a little of that one will renormalize the W mass, will renormalize the Z mass. These coefficients will renormalize the W mass. This coefficient, of course, contributes to the relevant value of alpha. So 3 of these coefficients are already subtractions I made in the theory when I defined, as I will do in the second line here, alpha, G Fermi, and MZ. So that leaves 3 coefficients which are independent of that renormalization. And then those coefficients are just 3 coefficients that represent possible new physics effects. So Takeuchi and I gave those some canonical definitions, which let me just write down. We defined S to be, and these are totally arbitrary prefactors. 16 over mz, I guess the simplest way to write it is pi 3 prime at 0 minus pi 3q prime of 0. T as 4 pi over sine squared theta w mw squared. Is that right? Yeah. Pi 1 of 0 minus pi 3 of 0. And u equal to 16 pi over mz. Sorry, that shouldn't be there. 16 pi pi 1 1 prime minus pi 3 3 prime. Okay. These are definitions that really assume that these q squared over m squared effects are very small. You'll find other definitions in more or less any place you look, especially if you look in the particle data book. You'll find very different definitions. But they all reduce to this in the limit that the new physics is very heavy. Yes?
Can you please repeat what the 3's and 1's are in your diagram?
Oh, so the 3 is the current J mu 3 left, and the 1 is the current J1 left. And remember that the W current is J1 plus I J2. So I call it 1 just to remove some extra factor to the square root of 2, which would otherwise appear. Okay. Okay, now this is really cool because pi 1 1 renormalizes the W mass. Pi 3 3 of 0 renormalizes the Z mass. But those renormalizations are linked by SU2 gauge symmetry. So if you take the difference, you get a finite result. Similarly, Q is equal to 3 plus y, I3 plus y. The y, the contribution to this term is finite because at very short distances, there's no interaction between SU3 and hypercharge. And the 3, the infinite term would cancel between these two. And here, it's basically the same thing. This is an SU2 relation, that quantity is finite. So it turns out that when you compute these things in perturbation theory, these are finite corrections, which then represent effects of new physics that are not removed by renormalization. And so that's pretty cool. Let me just notice that T has to do with isospin breaking by new physics. S has to do with the q squared over m squared term. That is to say, the amount of new physics, the bulk of new physics that contributes in the vacuum polarization diagram. U has both effects. And so if this is small and this is small, U should be doubly small. And in fact, in most models, that's the way it works. This can be an order alpha effect. This can be an order alpha effect. This one is order alpha squared. And it's conventional to ignore U. And I'll give you a much better argument for that in lecture number 4. But usually when you compute these things, U turns out to be tiny. Well, now we're down to 2 parameters. So this is really fantastic because you can draw 2 parameters on a piece of paper. And then you can represent explicitly the success or failure of the standard model. You had a question.
When you have derivatives in one case and non-derivatives in another one, it's derivative, right?
Sorry?
Yeah, it's the derivative, right? You have a prime.
So this is a derivative. This is not a derivative. It has to do with the fact that B and E can be non-zero and different. But because of SU2 symmetry, their infinite parts are equal. It's only the finite parts that are different. And this corresponds to what's called custodial SU2 breaking. An example is the top quark is heavier than the bottom quark. So the top quark loops and bottom quark loops will contribute differently to these and give different contributions to E and B. However, the infinite parts of those diagrams will be the same. Now, S really has to do with these coefficients. Actually, it is the difference between this coefficient and that coefficient. And again, those are related by the relation that Q is mainly isospin, but it has hypercharge. But the hypercharge contribution in here is finite. Okay, so there's a physical interpretation to this. And then another nice thing is that when you sort out all the renormalization conventions and everything, and you just ask, what is the effect of these parameters on electroweak observables, you can derive formulae like these. mw squared over mz squared minus the cosine squared theta w, which is given by this scheme, is a linear combination of S and T. Oh, I didn't quite leave myself enough room to write that out there. Let me write those things. Oh, let me just erase U. Good. Now I have room here. mw squared over mz squared, assuming that S and T are non-zero and U is 0, has a very simple form. It's alpha c squared over c squared minus s squared times minus a half s plus t and oh, I still didn't leave myself enough room. S star squared is equal to S0 squared plus alpha over CW squared plus SW squared. Oh, now is this okay? I violated the unitarity bound, the infrared bound. 1/4 S plus sine squared theta W times T. Sorry. Okay. Well, that's very cool, because now the business of comparing electroweak data to new physics has gotten very simple. You compute S and T. It has effects that are given by formulae like these on all the electroweak observables. You draw the ST plane. Every constraint gives you a band of some kind in the ST plane. If you have several of these bands, they might overlap, giving you a confidence region. And then you stay up nights praying that the standard model lives outside this confidence region. But, of course, that's not what happened. Let me just say that it turns out that these variables are also very useful for looking at the top and Higgs effects on precision electroweak. Yes?
What are all the constants in those formulas?
I'm sorry?
The constants in these formulas, C0, C...
Okay, so I defined S0 by this formula. Okay? C0 is the corresponding cosine of theta W. That 1 minus s squared, the square root of that. Then what you do is you write the expression for MW in terms of vacuum polarizations. You expand it using the various definitions on the blackboard. You renormalize so that these three quantities have their physical values. They also have expansions in terms of vacuum polarizations. You cover a page with vacuum polarizations. Everything cancels. And what you're left with is a linear combination of ST and U. Okay?
And why the cosine squared plus sine squared?
Minus.
And in the second one,
It's just the way it works out.
no, but in the second formula.
Oh, no.
It's a minus.
It's because I made a mistake. Okay.
So then
Yes.
that coefficient in the standard model will be the difference between the ceiling definition and and the second definition of the weak angle. I mean,
Okay.
Because in there you have
Oh, and maybe I should say that these things are only the new physics contributions. The standard model is what it is. Okay. So if S and T are 0, that's the standard model. Okay. And then any deviations from the standard model are parametrized like this. Okay. And then it turned out that Technicolor gave very large contributions to S. Something found also by many other people, Lisa Randall, Bob Hold'em, other people who worked on this. But this turned out to be a nice way to codify the failure of Technicolor models to agree with the standard model. It's also possible to represent the effect of the Higgs and the top quark, which had not been discovered at this time in terms of S and T. In particular, let me just note that, and I'll come back to this at the end of the lecture, that the contribution of S from the top quark is proportional to the log of mt squared. And the contribution of t from the top quark is proportional to mt squared over mw squared. It can be a very large effect. And in fact, that you probably know, if you know anything about precision electroweak, that the top quark and Higgs renormalizations are two rather large effects at the level of the current precision. So I'll come back and discuss these points at the very end of the lecture. It's interesting that this large ratio appears, and you should be asking yourself why such a large ratio can appear in perturbation theory. And that's a subject I'll begin to discuss in a moment. Okay. So finally, I guess I'd like to show you the evolution of the Esti Fit over time. It's way at the end of this set of slides. So here are the definitions. I'll just turn this off a little so we can see it. Those are almost the definitions I wrote on the blackboard. Here's the Esti Fit from our 1991 paper. And as you see, the top has a very large excursion as a function of, T has a large excursion as a function of m top, which is basically given by that strong dependence that I wrote on the blackboard. So one could actually try to predict the top quark mass from this kind of a diagram. We were not the first to do this, but it's kind of obvious from this diagram that the top quark has to lie in this region, which is about 160 to 180 GeV. The Technicolor models, as I said, gave large excursions in the positive direction in S. Here was the central value of the electroweak fit at that time. So they were totally wiped off the map. Here's a later version, basically after the 20 million Z's had been collected and the full data analysis had been done. Also, the top quark had been discovered. So we removed the top quark from the diagram, but the Higgs was still not discovered. The S and T parameters depend logarithmically on the Higgs mass. And so as a function of the Higgs mass, they trace out a curve like this in this diagram. So this is the standard model with various values of the Higgs mass, represented in terms of the standard model with a 100 GeV Higgs mass in terms of the S and T parameters. You see here how the best measured electroweak observables, sine squared theta W, MW, and the leptonic width of the Z, come together to really pick out a very definite region in the space that is preferred by experiment. And then the standard model, at least for low Higgs mass, lives in that region. And so the standard model works. Also, you could say, you could use this diagram to predict the Higgs mass. And indeed, based on similar analyses, the LEP electroweak working group said the Higgs mass must be below 144 GeV. And finally, here's the Esti diagram today. So again, showing the contributions from the W mass, the Z width, and that narrow red band is the electroweak asymmetries. And now the scale of this has decreased by about a factor of 5. So we have some very precise limitations on how much new physics can contribute to precision electroweak. Basically, we've moved the region where this heavy new physics can occur from a few hundred GeV into the multi-TeV region, which is also, unfortunately, where we are with LHC. Okay? So it's an interesting formalism. It might be useful to you, so maybe it's worth reviewing. And I'll come back to it a little at the very end of the talk. So now let's go ahead and talk about the thing that I had promised to talk to you about today. Actually, it's also relevant to this calculation that I've just described. Oh, sorry, no, that's not the right thing. Okay. Because it has to do with this question of the appearance in perturbation theory, and actually also in tree-level expressions, of powers of mt over mw. So mt over mw, in principle, it's the square root of 2, we know now. But, sorry, no, it's not the square root of 2. It's basically a factor of 2. It can be squared. It can be a large number. In principle, the top quark could have been heavier. The standard model, at least up until the LHC ran, allowed heavy quarks of mass up to 600 GeV. So then you would get m fourth generation squared over mw squared. That would be a really large number. So why does that number appear in perturbation theory? And maybe some of you know the answer to this question or would like to guess the answer to this question. Not a one. So think about it. I'm going to suggest a reason why it appears in certain tree diagrams. And we'll get back at the end of the lecture to the question of why it appears in one-loop diagrams. Here, let me get these lights back on. Okay. Now, there's one way that mt over mw, or some large number over mw, will appear in tree diagrams. And that's when you emit a W boson. So I'd like to now think about processes where you have some collider process where things come together and a W boson gets emitted with very large velocity. And you would think that the value of this diagram would be g squared or alpha weak to some power, and that otherwise you could just estimate the value of that diagram from kinematic invariance. And that may or may not be true, but let me give you an argument that it's not true. And then in this lecture, I'd like to explore whether that argument is valid or not. So let's think about the polarization states of the W boson. First of all, let's consider a W at rest. But I'm going to choose the 3 direction. And eventually, I'm going to take the W at rest and boost it in the 3 direction. And eventually, I want to consider very large boosts. So let's write the polarization vectors for a W boson, which is at rest with respect to angular momenta measured around the 3-axis. And this is a pretty straightforward thing to do. There are 3 vectors that represent angular momentum plus 1, angular momentum 0, and angular momentum minus 1. These are the 4-vector polarizations. Okay. So very good. Nothing unusual about that. And in the W rest frame, these 3 states are equivalent. They're the same visible length, if you like, and you can rotate them into one another. However, let's now boost to a momentum EP. In that case, 2 of these vectors will stay the same. Epsilon plus or minus will be 0, 1 plus or minus I, 0, because if I boost a transverse vector, it doesn't change. However, if I boost this vector, it turns into the following thing: 1 over mw p 0, 0, e. Okay. So this is a perfectly good choice for a polarization vector. If you dot the polarization vector into the momentum vector, you get 0. EP minus EP is 0. Nevertheless, there's something weird about this vector, because its magnitude, the magnitude of its components, is increasing arbitrarily with the boost. So it's essentially E over m at very large values of the boost. And that might have you think that E over m factors appear in tree amplitudes, and maybe even worse in one-loop amplitudes. So let me give you a little example of how you can get into trouble with this. Let's think about the process E plus E minus to W plus W minus. And let's try and estimate the cross-section for this process on the basis of one Feynman diagram. So let's have a photon or a Z here. Let's produce W plus W minus. The amplitude for this diagram, the cross-section for this diagram, is going to be something like alpha over, I wrote this down. Maybe I should write this down correctly. Yeah. So the scattering amplitude for this diagram is I e squared alpha over I e squared over S. And then there would be a factor of the epsilon minus the polarization vector of the W or Z, which we derived yesterday, K plus minus K minus, something like that. That's what you would have for a scalar particle. Actually, there's another factor of 2. So for scalar particles here, you would have this expression. If you have vector particles, you have to do something with the W polarizations. And maybe I should say this leads to a cross-section which goes like pi alpha squared over S. So now we have to do something with the W polarizations. And a simple thing to do is to dot them into each other. If we dot the transverse polarizations into each other, we'll get numbers of order 1. And this cross-section will be extremely well behaved. However, if we choose the longitudinal polarization state for the W's, we end up in trouble. Because this dot product will be this vector dotted into the reversed vector. And the answer is E squared plus P squared divided by MW squared. Okay, well that's not good. This is basically S over MW squared, and the cross-section goes like S over MW squared squared. Now, this is a point-like cross-section. It's going through an S-channel resonance. So unitarity says that this cross-section can only grow as large as 1 over S at asymptotic S. And that is being totally violated by this expression. Nevertheless, I didn't do anything wrong, did I? So this is a question that we have to address. If you have these longitudinal polarization vectors, they have elements which are proportional to E over MW. And E over MW can become as large as you like. So in physical predictions, are those elements there or not? And this is a question that I'd now like to explore. I'm hoping for some enlightenment from the audience. Sorry? There are more diagrams, yeah. So eventually, this might be solved if there are more diagrams. But it's not clear why it should be solved if there are more diagrams, because, I mean, there's one diagram that's very large. Are the other diagrams going to come and cancel it automatically? Maybe we need a principle for that. Okay. Okay. Well, the answer is you're absolutely right. Yes. I'm sorry?
So this is longitudinal polarization, right?
Yes. So?
It's related to the fact that so only the massive gauge bosons can have longitudinal polarization.
Yeah, but these are massive gauge bosons. Yes, please.
The gold, since the massive part comes from the Goldstone modes, like something to do with the Goldstone boson being eaten.
Yes. actually. So that's the next thing I'm going to say. Yes, you have something to say in the back. I'm sorry? No, these are all physical amplitudes. I mean, if I were computing loops, there'd be some extra polarizations, which would be canceled by the ghost states. But I'm not there yet. I'm just at the tree level. And I'm only looking at the physical amplitudes. But the other two comments are correct. A, the other diagrams will cancel this contribution exactly. And B, that has to do with the fact that the longitudinal polarization state of a W boson comes from the fact that the W ate a Goldstone boson. So let's be a little more precise about that. This is all encompassed by a very beautiful result called the Goldstone boson equivalence theorem. The Goldstone boson equivalence theorem says the following, that if you have a matrix element of x goes to y plus a W boson of momentum p, that becomes asymptotically equal to the matrix element for x goes to y plus the Goldstone boson of the standard model that the W8, and this is a W0, a longitudinal W boson. As the W is boosted, it more and more resembles the Goldstone boson that it ate to the exclusion of anything else. And so this amplitude is asymptotically equal to this amplitude with corrections that are of order MW over P. And so the formula was originally derived by Cornwell and Tektopoulos and Vianakis. Those papers are not so easy to read, as someone in this school has already told me. There's a very beautiful proof of this relation, which actually applies to multiple boosted W bosons by Chanowitz and Gaillard. And if you look in the lecture notes on the Indico page, you'll find the reference to that paper. It's a somewhat formal proof. It involves BRST quantization and ghosts and all that superstructure. I'm not going to give the proof to you here. Instead, I'd like to work out some examples. And we'll see that the examples are subtle. Sometimes you get the enhancement, sometimes you don't. And you have to think about what the Goldstone bosons are doing to decide whether or not the enhancement is there. Okay? There's a lot of computation in these examples, and I think I don't really have time to do it, but all the explicit computations are in the lecture notes. So if you find this interesting, you can go to the lecture notes and follow the computations there. So let's first take a very easy example, but also an interesting one, namely the decay of the top quark to BW+. In this analysis, I'm going to ignore the mass of the bottom quark, and I'm going to also take the top quark mass to be very large. So in principle, what should happen is the following. There should basically be 3 modes of decay to a W of helicity equals +1, to a W of helicity equals -1, and a W of helicity equals 0. This mode should have MT over MW enhancements in the amplitude, if this picture is right. The other two should be normal. And actually, it's not hard to do an explicit computation to find out what's what. So let me write the amplitude. Is equal to G U dagger for the bottom quark, sigma dot epsilon star for the W, U for the top quark. Square root of 2. Let me choose the following coordinates, which are very useful. I'm going to let the top quark have some arbitrary polarization. So I'm just going to represent it by a spinner. U of t. These are left-handed, so it's the square root of mt times that spinner. And I can ignore this part because of v minus a. The bottom quark I'm going to take to move along the negative 3 axis. The bottom quark is left-handed, and so UL of b is the square root of 2mb times minus 1, 0. And I'm going to ignore the mass of the bottom quark, because that's much less than any of the other masses in the problem. And now we just have to compute this sigma dot epsilon star for the various polarization states. Okay. So let's first do this for a helicity equals plus. Then epsilon star has a minus sign in it. Sigma dot epsilon star will be the lowering will be proportional to the lowering sigma matrix. And actually, between these two vectors, an arbitrary Xi and something that's raised, this will give the matrix element equal to 0. That's actually good because it's very easily explained. And the W will go this way, of course. So let's just make a little diagram here. The B left is left-handed, so its angular momentum points that way. The W, if it has positive helicity, also has angular momentum pointing that way. That's a spin 3/2 system. Okay, a spin 1/2 system cannot decay into a spin 3/2 system, so we're on the right track. Now, helicity minus 1, I'm going to get something proportional to the raising vector. So I'm going to get an m proportional to g. There'll be some factors, and then it'll be the upper component of Xi. So let me write Xi as cosine theta sine theta over 2. And so there'll be a cosine theta over 2 here. It's the raising one. It's sine theta over 2. That's better. So in that case, the W polarization points this way. The top quark polarization that it likes points that way. And so the bottom quark comes out in the direction of the top quark polarization. Now finally, h equals 0. Okay, well, looking at the vector over there, there's some p's here. There's a plus e and a minus e here. The b will overlap with this contribution. So I'm going to get g, I'm going to get the other component, cosine theta over 2. And I'm going to get p plus e, which is m top over mw. So there really is an enhancement there. And so now if you were to do all the factors correctly and write down the complete answer, what you would find is the following set of formulae. Maybe I can get rid of these now. Gamma of t goes to bw is equal to alpha weak over 8 mt times the 1 minus mw squared over mt squared for the w helicity minus. For helicity 0, alpha w over 8 mt times 1 minus mw squared over mt squared times an extra factor of, which is just the one that we found here, mt squared over 2 mw squared. And this has an interesting implication, that if you're at the LHC, you'll see the W because it decays to a lepton and a neutrino. A transversely polarized W plus will decay to a forward or a hard lepton. Sorry, I got that wrong. If you look at the energy of the lepton for a boosted W, the positive helicity W's decay to hard leptons, the negative helicity W's decay to soft leptons, and the longitudinal W's decay to leptons in the middle. And so you can actually, by reconstructing the event and measuring the lepton distribution, energy distribution, you can interpret the polarization state of the W. And by using this analysis, you can check the prediction from here that the decay rate to a longitudinal W over the total decay rate should be this factor of mt squared over 2mw squared divided by that plus 1, which is 70%. And against LHC data, this just works extremely well. So I even want to show you that, but to do that I need to hopefully get this. Oh, what am I supposed to do? I'm supposed to get rid of this. Oof. Sorry? Oh, I'm sorry. It's this tab. Oh, you set it up for me. Thank you very much. Oh, I guess I have to do something.
Boson. Yeah.
Okay. Excuse me. Here we go. We're good. No, this is what I wanted. Yeah, okay. So this is what I just told you. And now here's an analysis that was done by CDF, which is very clear. I mean, the problem is always that the low energy leptons have poor acceptance. And so you have to correct for that. And so after you correct for that, this beautiful diagram looks more like this. But you can see that the left-handed longitudinal and the red is helicity plus 1, the green is helicity 0, the blue is helicity minus 1, the black line is, with the acceptance of the CDF experiment, the combination of those that corresponds to this prediction. And then the bottom slide shows the data, which shows it works well at the 10 or 20% level. At the LHC, even at 7 TeV, here is the corresponding curve. And the data is compared to the standard model prediction, which is this one, and it works extremely well. So this is an interesting test case. We predicted the enhancement from the form of the longitudinal polarization vector. We computed and we found the enhancement is really there in the standard model prediction. We compare to experiment. By golly, it's really there. So now this seems extremely cool. It's evidence that these enhancements do actually appear. Now, the next question is, what's the significance of this term by which the longitudinal polarizations are enhanced? Well, let me write it over here, mt squared over 2mw squared. Now, remember that mt is proportional to the top Yukawa coupling, and mw is proportional to the gauge boson coupling, G, both times V. So if I write this as the top Yukawa coupling squared over G squared, the V's cancel out, and it's exactly this ratio. And even the factor of 2 gets swallowed up when you write this expression. So the data says it. The longitudinal W knows that it's really a Goldstone boson, and it's really supposed to couple with the top quark Yukawa coupling rather than this stupid SU2 coupling, which is much smaller. And that's why it's enhanced. So that's an interesting moral to take away from this example. This can actually happen, that when a top quark appears when a boosted W appears in a tree diagram or even in a loop diagram, as we'll see, it can be enhanced by some factor which is basically the reflection of the fact that the W thinks it's a Goldstone boson that couples with a Yukawa coupling, rather than an ordinary W boson that only couples with an SU2 coupling. Okay, time marches on, so I'm going to go rather quickly through the process E plus E minus to W plus W minus. And maybe we should first ask, I had some analysis over here where I looked at one Feynman diagram and I said that Feynman diagram is somehow illegitimate because for longitudinal W's, it grows like S over mW squared faster than it ought to be growing. Now, as you correctly pointed out, there are two more Feynman diagrams. So first of all, I can exchange gamma and Z. And secondly, there's a diagram with neutrinos in the T channel. And there is the possibility of cancellation among those diagrams. So looking at one diagram is not enough. It never is. But a question that we can ask is, what does the Goldstone boson equivalence theorem say about this process? So probably the first thing we should do is ask, what are the Feynman diagrams by which E plus E minus can produce a pair of Goldstone bosons? And actually, there are very simple diagrams. There's gamma plus Z going to a pair of Goldstone boson diagrams. And that's it. And the value here is just basically proportional to the rate for E plus E minus to create a pair of scalar particles times some appropriate factors of sine and cosine theta W. So this is what has to happen. It's not only that there are multiple diagrams and they can cancel, but they actually must cancel in order that the result of that diagram calculation agrees with the theorem. So now you can verify that explicitly, and I'll go through a little of it, but I think for the full details, you probably have to go to the notes. It's easiest, maybe, to look at right-handed electrons first. Because right-handed electrons don't couple to neutrinos, so we don't have to worry about this diagram. We only have to worry about these two diagrams, and they're basically of the same structure. And what happens in those diagrams can be described relatively simply. So there's a minus IE up there. There's an IE down here. There's There's some factors of 2e squared of 2 epsilon minus from the initial lepton state. We talked about that yesterday. This is dotted into something. Then there are the S-channel propagators, minus I over S for the photon, minus I over S minus mz squared for the Z boson. This comes with some factors which we need to work out. Here it's just E squared, E. Here it's going to be the following. The Z couples to the electron with I3 minus sine squared theta W times Q. So this is just going to be sine squared theta W. I3 is 0 for a right-handed electron, and Q is minus 1. This vertex, and then in the denominator, there's a CW squared. So, sorry. Let me go a little more slowly. This one is E squared. This diagram is E squared over SW squared. That is G squared over CW squared. So what goes here is S squared over S squared C squared. And then there's one more interesting thing that appears. If you compare the photon and Z vertices to W's, there's a CW over SW. Ooh. No, I'm sorry. I wrote this extremely badly. Let's try again. So there is minus SW squared over, it's just one, CWSW. So this is basically G over CW I3 minus sine squared theta W times Q. That's the factor that you know about. Then in this vertex, there's a relative factor CW over SW. And then what's very cool is that this entire factor turns out to be minus 1. And so asymptotically, there's a cancellation of these two diagrams in this channel. So it had to happen because the right-handed electron doesn't couple to SU2. It only couples to hypercharge. So the right-handed electron asymptotically will only couple to hypercharge. And hypercharge cannot couple to W bosons. So there must actually have been a perfect cancellation for right-handed electrons between these two diagrams. Okay, now we're halfway there. The other half comes when we look at left-handed electrons. So for left-handed electrons, there's a 1/2 here, which is not going to cancel. And so we have to then find some structure which will then relate that to the neutrino diagram. So this is now, well, let me say, somewhat ferocious calculation. So I'm not going to do it on the blackboard, but it is actually in the notes. What you want to do is asymptotically replace the W plus and W minus polarization vectors by K over MW, which is a good approximation in when the W's are very highly boosted and S is very large. Then you need to write down the Young-Mills vertex. And then there are various rearrangements that you can make with the Young-Mills vertex. Also in this diagram, when you have K over M dotted in here, you do the manipulations that you do to prove the word identity, which basically will eliminate the T-channel neutrino propagator. And then what you'll find is that the two expressions, the one from here and the one from here, are exactly equal and opposite and cancel in the asymptotic limit. It's a little harder to show in this case that what's left over is indeed the Goldstone boson result. So this approximation doesn't suffice to show that. But at least it's a fun exercise to show It's true, by the way, but it's just a little harder to show. But this argument it's quite straightforward, and you can work through the steps and see that after you make this approximation on both sides and make appropriate kinematic substitutions, that this diagram does cancel the sum of these, cancels the 1/2 piece. And there we go. Now the unitarity violation is gone, and this process is predicted to behave the way it ought to if it's to asymptote to the values of these diagrams in the end. Now, this has a very interesting implication as far as the actual value of this cross-section, which was measured at LEP. Of course, the accelerator LEP at CERN, after it did all this beautiful work at the Z, the energy was doubled, and eventually it ran at an energy of 208 GeV in the center of mass. Unfortunately, not quite far enough to discover the Higgs boson, although everyone was hoping for that, and it would have been very nice, but they didn't quite make it there. Nevertheless, 208 GeV is enough energy to produce W pairs for which the threshold is 160 GeV. And so then you can observe whether the measured cross-section indeed asymptotes to something reasonable, or whether it goes off to infinity violating unitarity. And here's the result. So the data points are the data, the average of the 4 LEP experiments for measurements between 160 and, as you see, 208 GeV. The blue curve is the result of the standard model calculation. There are a few percent radiative corrections, one-loop radiative corrections, which are actually taken into account in that curve. It doesn't really change it quantitatively. The other two curves are obtained in the following way. The lower curve is obtained by removing this diagram. And as you see, it's a total disaster with respect to agreement with the data. And the upper curve is including only the neutrino exchange diagram, as people might have done before they understood the full electroweak gauge theory. So you don't have SU2 cross U1, it's a disaster. You have SU2 cross U1, it's perfect. It's really a very beautiful success of the standard model. Okay. Now, there is one more thing that I wanted to discuss with you at the tree level, which is an interesting case. I'm not sure, Tao may talk to you a little about this, so maybe I should talk about it only briefly. But again, the full details are worked out in the notes. There's a case where you might think that the Goldstone boson equivalence theorem applies where it doesn't apply. And it's actually very important that it doesn't apply. So it's probably worth calling attention to in this lecture. And that's the case of collinear W radiation from a fast quark or lepton in a collider reaction. So let me give you the wrong argument and then tell you the correction to the argument. So here's the process we'd like to consider. I go to the LHC. I have some down quarks coming from one proton and an up quark coming from another proton. These quarks rush together, and being fermions, which are essentially massless, they can emit collinear radiation. So the D can emit a collinear W minus and turn into a U, and the U can emit a collinear W plus and turn into a D, after which the W minus and W plus can come together and make some reaction, which might, for example, include the production of one or more Higgs bosons. So this is something very interesting. The question I'd like to ask is, what are the polarizations of the W's, which obviously affect your analysis of this reaction? the Goldstone boson equivalence theorem seems to indicate that the W's are purely transverse. Because after all, the U to D, if it emits a Goldstone boson, this vertex is the Yukawa coupling of the up quark or the down quark, which are extremely small numbers. And so according to the Goldstone boson equivalence theorem, that can never happen. But, well, there's an out. Because the theorem is not precise about what goes in the denominator here. What actually should go there is PT, or the hardness of the reaction. Because there's always some frame that you can boost to where everything is at rest, or at least slow, with respect to everything else. And so if you imagine that the validity of the Goldstone boson equivalence theorem is measured by PT and not by the absolute momentum of the W, you could well imagine that you could produce longitudinal W's in this reaction, although probably there'll be something peculiar about them. And so, well, it's not hard to do the calculation directly. You folks, how many of you have actually gone through the analysis to derive the Altair-Parisi splitting functions for QCD? Raise your hand. Sorry? I'm sorry?
There's a homework assignment for that.
Oh, okay. Well, after Tao has gotten through with you, you'll know how to do this. Basically, it's really a very straightforward exercise. You make the approximation that you start with a quark with momentum, let's say, E 0, 0, 0. You have this split into two almost collinear pieces. In this case, the quark and the W boson, with momentum fractions E times 1 minus Z, 0, 0, E times 1 minus Z, and E, Z, E, Z. Now, this guy has to be on shell in that diagram. This guy has to be on shell. But it has some non-zero PT. So you have to write E times 1 minus Z minus PT squared over 2E times 1 minus Z. Okay. That puts it on shell to first order in PT. This one, you just have to, this is off shell, but you have to conserve energy. So now we have three definite momentum vectors for the three components. And now you just write down the polarization vectors. You embed those in the vertex, which is the splitting vertex. You compute the amplitude, you square it, you integrate over appropriate phase space, and you get the following answers, which I guess I only have time to just write for you. But as I say, the full derivation is in the notes. Okay, so what you find is that the cross-section for x plus y goes to, so let's call this, oh, maybe I should just say u plus d, goes to d plus u plus whatever is the final state, z up here, is equal in the first approximation, as you let pt get very small, to the integral dz plus and dz minus of f of z plus, f of z minus, times the cross-section for a W plus and W minus with the momentum fraction Z plus and Z minus going to Z. Okay. And, well, I guess by Z I didn't mean the Z boson. I meant whatever ends up there. Okay. So these things are W structure functions in the quark which you've computed perturbatively. And those W structure functions have the following behavior. Now I can erase this. For the transverse components, you find exactly the answer that you found in QCD. So for W plus and W minus, you find the integral d2 pt times pt squared times pt squared over plus mw squared times alpha w over 4 pi. Those of you who know a little QCD probably recognize that for quarks this would be alpha s over 2 pi times some Casimir. And then let's see, this is a left-handed U. So the one that follows the helicity is the minus, and that will have a 1 over x. And the F plus will have exactly the same thing times 1 minus x over 1 over z, 1 minus z over z. The interesting one is the longitudinal one. The factor over here is 1 minus z squared over z. The factor here is mw. So when a quark radiates a gluon, the p-t distribution has a long tail. The gluon can be emitted at very large transverse momentum, and it's a logarithmically divergent integral, which is eventually cut off by kinematics. For the longitudinal W, when you get out in this region, the Goldstone boson equivalence theorem has started applying. And so the W can never get there. It's cut off more sharply, and in fact, this distribution is integrable as pt goes to infinity. But nevertheless, it's a finite result. And so with probability alpha w over 8 pi, you can indeed radiate longitudinal W's from fast quarks which are coming into a process. And that's very important. For example, that's what makes the W fusion cross-section in Higgs production as large as it is. Okay, we're coming very close to the end of the hour. There was one more thing that I wanted to talk about, but it's actually on the slides, and you can work through it yourself. Let me just tell you what the moral of that particular example is. I wanted to discuss the fact that these large effects of order mt squared over mw squared also arise in perturbation theory. And it's worth knowing about them because you will encounter these things when you do one-loop diagrams in the standard model. So very often in the standard model, if you have some one-loop diagram which involves the top quark and a W boson, you will find that this diagram has some ordinary pieces proportional to g squared and some not so ordinary pieces proportional to g squared mt squared over mw squared. And these reflect the fact that even at the one-loop level, the W that appears, perhaps even on an external state, can be treated by the top quark as if it is a Higgs boson rather than a W boson. And you can find the coupling being the top quark Yukawa coupling rather than the ordinary gauge coupling. One example of this I've already told you about. The T parameter of precision electroweak is some factor which I might as well write it on these slides. Yeah. 3 over 16 pi SW squared MW squared times MT squared. So this is the result of the one loop diagram where you just take top quark loops and bottom quark loops and you evaluate the expressions that I wrote at the beginning of the lecture. You can do that evaluation quite directly. Ordinarily, you're used to vacuum polarization diagrams vanishing as q squared goes to 0. But if you have a W here, this is a chiral current, which is not conserved. And so it doesn't vanish. And in fact, not only doesn't it vanish, but the coupling here behaves like a Yukawa coupling instead of a gauge coupling. And so you end up with this result, which, as we've already seen, is a very influential effect in the precision electroweak calculations. This comes up also with a vengeance when you do flavor physics and compute one-loop diagrams, for example, in radiative B decays that involve top quarks. So it's something you should always be aware of, that it's not strange to find these enhancements. It's just a reflection of the fact that the top quark is some essential piece of the standard model, coupled to it by the Higgs boson, with a coupling which is actually the largest electroweak coupling in the standard model. Okay? As I say, if you want more details on any of this stuff, you'll have the lecture notes on the Indico page. I'm still going to be around all week, so if you have any questions with that, come and ask me. And we'll pick up on Thursday with a more detailed examination of the Higgs boson itself. Okay, see you then.